Consider a function f of n variables subject to m constraints. These constraints are given by the equalities that we obtain by equating certain constraint functions g to their respective constants. Within the space defined by the constraint equations, we wish to find the critical points of the objective function f. We will combine the objective function and the constraints in the so-called Lagrange function, which you see below. It consists of the function f plus the sum of new extra variables called Lagrange multipliers multiplied by each of the expressions that we obtain after having moved all the terms of each constraint equation to one side. So the Lagrange function depends on the n original variables and the m new Lagrange multipliers. In order to find the critical points of the objective function subject to its constraints, we take the Lagrange function, set all first-order partial derivatives equal to 0, and solve the system of equations. Once we have all the critical points, we wish to determine their type. Here, we will see a method that uses the bordered Hessian matrix. In general, if the objective function has n variables and there are m constraints, the bordered Hessian matrix is an m plus n by m plus n matrix, and its entries may depend on all the original variables and all the Lagrange multipliers. Sometimes it can be helpful to think of the bordered Hessian as a matrix with 4 blocks. Top left, we will always have an m by m block of zeros. Top right, we will place along each row the first-order partial derivatives of each constraint function with respect to all original variables. Bottom left, we write the same values as in the top right block, but this time along each column, like a transposed block. Finally, bottom right, we place the second-order partial derivatives of the Lagrange function with respect to all original variables. For the critical point classification method that we are going to see in this video, we are specifically interested in analyzing the leading principal minors of the bordered Hessian matrix. The kth leading principal minor is the determinant of the upper left k by k submatrix. We must compute the determinants of submatrices of this form. However, we will only need to calculate the leading principal minors from the one of order 2m plus 1 to the one of order m plus n, which is the determinant of the full bordered Hessian matrix. So the method for classifying critical points is as follows. If you have the bordered Hessian matrix depending on the original variables x1, x2, x3, etc., and the Lagrange multipliers lambda 1, lambda 2, lambda 3, etc., the first step is to evaluate it at each critical point that you want to analyze. Then you have to compute the leading principal minors between the one of order 2m plus 1 and the one of order m plus n. This makes a total of n minus m leading principal minors to calculate. And by the way, we only care about the signs of these calculated leading principal minors. According to the sequence of signs that you obtain, check in which case we are according to some rules. Case 1. All calculated leading principal minors have the same sign as negative 1 to the m. Then the critical point is a local minimum. Case 2. The leading principal minor of order 2m plus 1, which is the smallest order that we need to consider, has the same sign as negative 1 to the m plus 1, and the subsequent leading principal minors alternate in sign. Then the critical point is a local maximum. Case 3. All calculated leading principal minors are non-zero, but the conditions of case 1 and case 2 are not met. Then the critical point is a saddle point. Now, let's walk through a complete example. In this case, we have an objective function f of x, y, z equal to x cubed plus y cubed plus z. And we have one constraint, which is that 3x plus 3y squared plus z, this is our function g, is equal to 1. So 3 variables means n equal to 3, and one constraint means m equal to 1. We build the Lagrange function, which is f plus a Lagrange multiplier lambda multiplied by the expression that we obtain after having moved the constraint function g and its constant to the left side of its equation. This Lagrange function depends on the 3 original variables and on the new Lagrange multiplier. Therefore, in order to find the critical points, we compute the 4 possible first-order partial derivatives with respect to all variables, and we set the equations equal to 0. This produces a system of equations whose solutions are the critical points. In this case, you can easily conclude that there are 4 solutions. That is 4 critical points that you can see right here with their values for x, y, z, and lambda. Now, it's time to build the bordered Hessian matrix that we will use to classify the 4 critical points. There are 3 original variables plus 1 Lagrange multiplier, so the bordered Hessian will be a 4 by 4 matrix. Since there is only one constraint, the block of zeros at the top left is just a single 0. Contiguous to that 0, we place the first order partial derivatives of the constraint function along the first row and also along the first column. Finally, we have this block here where we write the second order partial derivatives of the Lagrange function with respect to the original variables. You can see the final result on the right. Now, we have to decide which leading principal minors we are going to compute. The first leading principal minor that you must always consider is the one of order 2m plus 1. And the last leading principal minor will always be the one of order m plus n, which is the determinant of the full bordered Hessian matrix. In this case, n is equal to 3 and m is equal to 1. So we only have to consider the third leading principal minor, which is the determinant of this 3 by 3 matrix, and the fourth leading principal minor, which is the determinant of this 4 by 4 matrix. Now that you know how to use the matrix, let's evaluate it at each critical point and apply the criterion. Consider the critical point -1, 0, 4. Substitute its values in the bordered Hessian matrix so you obtain the specific matrix that you see on the right. Now we compute the 2 leading principal minors that we need in this case. First, the determinant of the upper left 3 by 3 matrix, which happens to be positive. Then the determinant of the full 4 by 4 matrix, which happens to be negative. Now, go back if you need, but we actually are in case 2 of the criterion because the calculated leading principal minor of smallest size has the same sign as -1 to the m plus 1, which is positive, and the subsequent leading principal minors alternate in sign. Thus, the critical point -1, 0, 4 is a local maximum of the constraint objective function. In general, if the number of constraints is odd, the alternation of signs that indicates the presence of a local maximum is positive, negative, and so on, which is the case that we just verified here. However, keep in mind that in a different problem, if the number of constraints were even, the pattern for a local maximum would be negative, positive, and so on. Consider the critical point -1, 2, -8, and evaluate the bounded Hessian matrix at it, so you get the specific matrix on the right. Compute the third leading principal minor, and you will see that it is positive. Compute the fourth leading principal minor, and you will see that it is also positive. However, according to our criterion, you will see that we are not in case 1, because not all calculated leading principal minors have the same sign as -1 to the m. Obviously, we didn't obtain two negative determinants. Neither are we in case 2, because there is not an alternation in the signs of the determinants, starting with a minor with a sign of -1 to the m plus 1. Given that all calculated determinants are non-zero and the conditions of case 1 and case 2 are not met, we are in case 3, and the critical point -1 to -8 is a saddle point of the constraint objective function. For the critical point 1, 0, -2, proceed as usual. Evaluate the bounded Hessian matrix at this point, and you get the specific matrix on the right. Compute the third leading principal minor, and you will see that it is positive. Compute the fourth leading principal minor, and you will see that it is also positive. As before, all calculated leading principal minors are non-zero, and they do not satisfy the conditions of case 1 and case 2 in our criterion. So, the critical point 1, 0, -2 is another saddle point of the constraint objective function. Finally, evaluate the bounded Hessian matrix at the critical point 1, 2, -14, and you will have the specific matrix on the right. The third leading principal minor is negative, and the fourth leading principal minor is also negative. Now, this corresponds to case 1 in our criterion, because all calculated leading principal minors have the same sign as -1 to the m, which is negative in this problem. Therefore, the critical point 1 to -14 is a local minimum of the constraint objective function. As we have seen here, if the number of constraints is odd and all the calculated leading principal minors are negative, this indicates the presence of a local minimum. However, keep in mind that in a different problem, if the number of constraints were even, the pattern for concluding that there is a local minimum would be that all calculated leading principal minors were positive. In conclusion, we were able to find all the critical points of our three-variable objective function subject to one constraint. In particular, we found one local maximum, two saddle points, and one local minimum of the constraint objective function. Here you have a summary. As a final tip, make sure you understand correctly the statements of the criterion explained in this video. Depending on the number of variables n and the number of constraints m, the application changes completely, since the number of determinants you need and the interpretation of their signs will be very different in each problem.